Hi everyone! In this video we're going to learn about operations that we can perform on functions. Most operations we already know. These are addition, subtraction, multiplication, and division. But there is one operation that we only apply to functions. It's called composition. Functions can be composed with each other. We're going to learn how this operation works. Let's start with the first three basic operations. There are sum, difference, and product. Basically, when we add two functions, subtract two functions, or multiply two functions, we obtain a new function. What can we say about the domain of such function? It's actually pretty simple. For functions f plus g, f minus g, and f times g, the domains consist of the numbers x that are in the domains of both f and g. Now, if that didn't sound too simple, let me illustrate this idea with a picture. If this yellow circle includes all values of x that are in the domain of f, all possible inputs for function f, and this blue circle includes all possible inputs of function g, in other words, domain of function g, then all those values that are in both domains, that's this overlap, are going to represent the domain of functions f plus g, f minus g, and f times g. Now let's talk about the division operation. One function can be divided by another function, and as a result, we obtain a new function. It's a quotient f over g. We just have to make a note that the function by which we divide is not a zero function. Otherwise, the result would be undefined. When it comes to the domain of this quotient f over g, the idea is very similar as with other three operations, with just one important note. For f over g, the domain consists of the numbers x such. For f over g, the domain consists of the numbers x that are in the domains of both f and g, except for the points where g of x equals 0. Let me illustrate that. So again, domain of f over g will include all values of x that are in both domain of f and the domain of g. But from this set, we have to exclude values of x that make function g equal 0 to ensure that function f over g does not become undefined. Let's try a few examples to better understand these operations and practice finding the domains. Here's the example. It says, suppose that f of x equals absolute value of x minus 3 and g of x equals square root of x. Find each given function and its domain. First, we need to find function f minus g of x. In this case, f minus g is the name of the new function. Well, to obtain such function, we simply have to take function f of x and subtract function g of x. So function f minus g of x equals absolute value of x minus 3, that's our function f of x, minus square root of x, that's function g of x. So you literally write each function with the minus sign in between them and simplify the expression if possible. In this case, we're not able to simplify this expression. So that's our answer for finding the function f minus g of x. And now we also need to find the domain of this function. Let me remind you how we find the domain. We have to look at the domain of function f, we have to look at the domain of function g, and find where they overlap. In other words, we need to find values of x that are in both domains. Let's describe the domain of function f. Function f is the absolute value function x minus 3. Remember, we just think if there are any restrictions to what x values can be. Is there anything that we cannot plug in for x and obtain the corresponding output? Not really. Any real number can be plugged in for x, and we can always subtract 3 from that number and then take the absolute value. So the domain of function f includes all real numbers. In other words, it's the interval from negative infinity to infinity. How about the domain of function g? Function g is square root of x. Well, we know that when we have square root or any radical with an even index, expression that's inside the radical should always stay positive or 0. Well, since it's just x inside the radical, it means that x has to be positive or 0, in other words, greater than or equal to 0. And that's the same as the interval from 0. 0 is being included, so that's why I'm using brackets, to infinity. And now let's think where these two intervals overlap. Well, you might already see the answer, but I'd like to show you the steps that you might want to take if the answer is not that obvious. So what you can do is to graph both intervals on the number line and see where they overlap. To graph the interval representing all real numbers on the number line, I just have to highlight the entire line. That's the domain of function f. And now on the same number line, I'm going to graph the second interval representing the domain of function g. So that's the interval from 0 to infinity. I'm going to use different color. Since 0 is included, I'm going to show a closed circle here. And then from 0 to infinity, that's everything that's greater than 0, so I will have to highlight to the right. So everything that's in red represents the graph of the interval from 0 included, to infinity. Where do those two intervals overlap? In other words, where do I have both colors on the graph? Well, it's over here. It's the overlap, or we can also say the intersection of the two intervals. And that means that this will represent the domain of the function f minus g. So domain of the function f minus g is the interval from 0 included, to infinity. Now let's try to find function f over g. That is simply function f of x over function g of x. And since function g of x is not a zero function, we're able to obtain the function f over g. F over g of x is the quotient of absolute value of x minus 3 and square root of x. Now what's going to be the domain of this function? Remember how we said that it also includes values of x that are in both domains of f and g. However, we have to exclude values of x that make function g of x equals 0. That's the function that's here on the bottom. We already found values of x that are in both domains, and it's right here. But what will make the denominator equal 0 in this case? Well, that's when x is 0, right? Plug in 0 here, square root of 0 is 0. So that means that 0 has to be excluded from the domain. So, long story short, we're going to use this interval, but we will exclude 0 from it. In other words, the domain of function f over g is the interval from 0 to infinity, where 0 is not included. So I added this note. Use this interval because it includes values of x that are in both domains of f and g, but exclude x equals 0 because it makes this denominator equal 0. With interval notation, we just use parentheses instead of brackets to indicate that 0 is not part of the interval. Now let's talk about this special operation that only applies to functions. It's called composition. And here it's shown how that operation is defined. The composition operation is denoted by this special symbol. Try not to confuse this with multiplication operation notation, which is just a dot. Here's a little circle. And we read this as f composed with g. This operation is defined in the following way. Composition of f and g is f of g of x. If this looks a little confusing, that's fine. I'll try to explain how it works. So basically what it says here is that function g of x is being plugged into the function f. Let me try to illustrate this. When we have the composition of functions f and g, its input x takes the following path. First, it's being plugged into function g. Let me show it on my picture. So x is an input. Then I'm going to write the output in function notation form. The output will be g of x. And then this output becomes an input for function f. So that's why we plug into function f. And this is why we write it as f of g of x. To better understand this process, we want to look at a few examples. But first, let's talk about the domain of the composition function. The domain of the composition function f composed with g is the set of all numbers x in the domain of g, such that g of x is in the domain of f. Now that, I'm sure, sounds a little confusing, so we'll just do a few examples to better understand what this means. And one more thing that I would like to note here is that composition operation is not commutative. That means that when we composed f and g in this order, the answer will be generally different from when we composed g and f in a different order. So that's similar to subtraction and division. For those two operations, we get different answers when we change the order of terms. This is how I can write it in short. So make this note. In our next example, we're given two functions f of x that equals x squared plus 1 and function g of x that equals square root of x plus 2. And we need to find each composition and state the domain. So notice that in the first case, we need to compose f and g. And in the second case, we have to compose g and f. So it's a different order. So we'll see how results will be different because of the different order. So to compose two functions, we start by writing the definition of this operation because it will help us to know what to do. The composition of functions f and g is the function f of g of x. So we basically keep the order of functions as they're given here. F composed with g, so f goes first, and then g is being plugged into f. That's why it's inside the parentheses. Well, in the next step, what I'll do, inside the parentheses here, I will replace the name g of x with the actual function. What is the function g of x? Well, it's square root of x plus 2. So that is function g. And now as I look at this resulting expression, f of square root of x plus 2, I know what to do because we already learned the function notation. Whatever stands inside the parentheses here has to be plugged into function f for every x. So in function f, there's only one place where we have x. It's right here, x squared. So that x has to be replaced with whatever I see inside the parentheses, so with that square root. Since x is being squared, that expression will have to be squared. And then the rest of the function is plus 1. So I'm going to write plus 1. So what we're looking at is function f with square root of x plus 2 being plugged in for x. And now we just have to simplify this. So we know that square cancels the square root. This means that we're just going to have x plus 2 and then plus 1. If I combine like terms, then I'll get x plus 3. So the composition function f composed with g of x equals x plus 3. That's our answer for the composition function. And now let's find the domain. Let me explain what the definition on the previous slide was talking about. So first, we focus on the domain of the resulting function. When we compose f and g, we obtain a new function, the composition function, and it's x plus 3. And it's just a linear function. So we know that the domain of a linear function includes all real numbers. However, we also need to consider the domain of function g. And this is because while the resulting composition function can work with all real numbers, in other words, input can be any real number here, we only want to keep the values of x that are in the domain of g, because if we use any values that are not in the domain of g, then we're simply not going to be able to produce this output, which later becomes the input of function f. Hopefully that makes sense. So in our example, while the resulting composition function can use any real number in its domain, we're going to make a note that function g does not work with all real numbers because of the square root that it has. So to find values in the domain of g, we have to make sure that expression inside the square root stays positive or 0. So basically we solve this little inequality where x plus 2 is greater than or equal to 0. That means that x is greater than or equal to negative 2. So I'll make a note here that domain of g is the interval from negative 2 to infinity. And therefore, the domain of the resulting composition function has to be restricted by this interval. So domain of f composed with g is the interval from negative 2 to infinity. Now let's try the second example. We need to compose g with f, so we're changing the order. First, I'm going to write out the definition of the composition of g and f. It's g of f of x. Remember, we write function names in the same order as they're given here. G goes first, and then f is inside the parentheses now. In the next step, I'm going to replace f of x inside the parentheses with the actual expression, which is x squared plus 1. So it's g, and then inside the parentheses, it's x squared plus 1. And now this notation, g of x squared plus 1, tells me that I have to take expression x squared plus 1 and plug that into function g for every x. In function g, I only have one place where I see x, right here. So this x is going to be replaced with x squared plus 1. So I have square root, and instead of x, I'm writing x squared plus 1, and then plus 2. I will simplify this expression by combining 1 and 2, so that's going to be x squared plus 3. So the composition function g composed with f of x is the square root of x squared plus 3. And as you can see, the result is different compared to when we composed functions f and g in that order. Now, what is the domain of this function? Once again, first we focus on the domain of the resulting function. And it's a square root function, and we just said that when we have a square root function, we want to make sure that expression inside the radical stays positive or 0. Well, in this case, since it's x squared plus 3, that will always stay positive, no matter what x I use, positive or negative or 0. Once I square it, it will be always positive or 0 if I plug in 0, but then I add 3. So this expression is always positive for all x. So that means that we can use any real number for this resulting function. However, let's check the domain of function f this time. So we always check the domain of the function that's being plugged in here, or the one that's in the second place. And that's because when x begins its path, first it gets into function f in this case. So we want to make sure that we stay within the domain of function f. Now, what is function f? It's x squared plus 1. It's a quadratic function, but we can see that nothing can go wrong with it, no matter what x we use. So domain of this function f includes all real numbers. So since there are no restrictions for function f, and we see that there are no restrictions for function g composed with f, we can use any positive. That means that the domain of the composition function g composed with f includes all real numbers. In other words, the domain is the interval from negative infinity to positive infinity.